Physics Part 349. As the disk spins, it cuts through the flux lines of the magnet. This cutting becomes more obvious if a radius of the disk is considered. As the radius rotates, it will cut flux when EMF will be induced in the disk, but because the rate of cutting flux varies from one part of the disk to another, the EMF will have different magnitude in different regions. The disk is metal and therefore electrons will move between the regions with different EMF values. Currents are induced in the disk. Since these currents vary in the magnitude and directions, they are called eddy currents. The eddy currents disk is referred to as eddy current damping. If the permanent magnet in the figure is replaced by an electromagnet, the spinning disk will be slowed down whenever there is a current in the electromagnet. This is the principle behind electromagnetic braking. The advantage over conventional brakes is that there is no physical contact with the spinning disk. This makes such brakes very useful for trains traveling at high speeds. However, the advantage is that the disk slows down. The induced eddy currents will be smaller and therefore the braking will be less efficient. This system would use this system would be useless as the parking brakes on a car. We've got an example for you. The uniform flux density between the poles of a magnet is 0.080 Tesla. A small coil of the area of cross section 6.5 centimeter square has 250 turns and is placed with its plane normal to the magnetic field. The coil is withdrawn from the field in a time of 0.26 s. Determine the magnetic flux through the coil when it is between the poles of the magnet. Determine the change in magnetic flux linkage when the coil is removed from the average from the field. Determine the average EMF induced in the coil whilst it is being withdrawn. Now it's your turn. An aircraft has a wingspan of 17 meters and is flying horizontally in a northerly direction at a speed of 94 meters per second. The vertical component of the Earth's magnetic field is 40 U Tesla in a downward direction. Calculate the area swept out per second by the wings. Calculate the magnetic flux cut per second by the wings. Calculate the EMF induced between the wing tips. State which wing tip will be at the higher potential. Example number 2. A current carrying solenoid produces a uniform magnetic flux of density 4.6 into 10 power raised to minus 2 Tesla along its axis. A small circular coil of the radius 1.2 centimeter has 350 turns of wire and is placed on the axis of the solenoid with its plane normal to the axis. Calculate the average EMF induced in the coil when the current in the solenoid is switched off in a time of 85 meters per second. Number 3. A metal disc is made to spin at 15 revolutions per second about an axis through its center normal to the plane of the disc. The disc has radius 24 centimeter and spins in a uniform magnetic field of flux